Assume that women's weights are normally distributed with a mean of 143 pounds and a standard deviation of 29 pounds, and that X bar is the mean of a sample of 10 women's weights. Pause the video for a second and try to answer each of these questions, and then I'll explain the answers. Question 1 says, if P, the probability that X is between A and B, equals 0.7203, which of the following is true? So we're just saying this is a distribution of individual women's weights. X represents the weight of one woman. So we're saying that the probability, or the area under this curve, is 0.7023. 72% of the women weigh between A and B pounds, in other words, according to this model. So which of the following is true? The probability that X bar, the mean of 10 weights, is between A and B is either greater than 0.7203, less than 0.7203, or equal to 0.7203. Well, let's think about what the distribution of X bar would look like. We know that it would be centered at 143 because we know that mu of X bar equals mu. We know that the standard deviation would be less because sigma of X bar would be 29 divided by the square root of 10, so it's going to be smaller spread. So if it has a smaller spread, that means everything is going to be clustered closer to the mean. If the distribution is thinner, it still has to have a total area under the curve of 1, so it's also going to have to be taller. So basically we're looking at a distribution that's going to look more like this. So now we're looking at the area under the curve between A and B, and we're wondering what percentage is between A and B. Is it going to be greater than 72% or less than 72%? It's not, or equal to 72%. Well, what might be helpful is to look at what's not under the curve, not between A and B. So if we look at the area that's not between A and B, we see that it is less than the area that was less than A and greater than B before. So this area must be greater. And that makes sense because there is a higher proportion of mean weights that are closer to 143 than individual weights that are closer to 143. So the correct answer is A. The probability that X bar is between A and B is greater than the probability that X is between A and B because X bar is going to be closer, the mean is going to be closer to the true mean than an individual would be on average. Okay, now second question. Right now we have that the probability that X is greater than B, in other words that it fits in this little area, is 0.0843. Now what we want to know is the probability that X bar is greater than B less than, greater than, or equal to 8%. So once again, let's draw our sampling distribution, which is going to be taller and narrower. So now we're looking at the proportion of values that are greater than B, and we can see clearly that it's going to be less than 8%. So the answer is B. It is more likely for X bar to be closer to the mean and less likely for X bar to be farther away from the mean than X. Now, just to show you what this looks like with a drawing that's drawn to scale more neatly, here is a drawn to scale model of the women's weights, the normal model for women's weights with mu of 143 and sigma of 29. You can see that the spread is from about maybe 55 to close to 240. And I asked the question in this problem, the probability that X is greater than 140. Well, if the mean is 143, we would expect the probability that X is greater than 140 to be just a little bigger than 50%, which it is. Okay, so that's that shaded region. So this is a distribution of X, individual women's weights. What is the probability that in a random sample of 100 women, the mean weight is greater than 140? Well, remember, we know that using any size sample, since the original population is normal, or approximately normal anyway, then the mean the distribution of sample means will also be approximately normal. Also, we have a large enough sample size that it wouldn't have mattered anyway. So we have mu of x bar is 143. Sigma of x bar is 29 divided by the square root of 100. I picked that nice number so we could easily figure out that sigma is 2.9. So now the distribution is, instead of being spread from 55 to 240, it's spread from about 130 to about maybe 160. Much smaller spread. So since the entire distribution is clustered more closely around the mean, we see that the probability of x bar being greater than 140 is now up to about 85%, because a greater proportion of the area is closer to 143. Now, what if I put these two graphs on the same scale? How would they look? Here would be the population of women's weights, and here's the sampling distribution of x bar. You can see how much thinner it is. It's 10 times thinner because its standard deviation is 1/10 as big. And so it's also 10 times taller than the original population was. So it's 10 times thinner and 10 times taller, and you can see now why such a high proportion of the women's weights are greater than or equal to 140. Problems like the ones we just saw down here are very similar to problems that you would see on an AP exam. So this kind of reasoning is really important. Make sure you understand these.